Hi, hope you are doing well, right? So, in our last video, what we actually did, um, we reproduced this graph that is actually, uh, sorry, we reproduced actually this graph that is actually phase matching curve. Okay, and we also see how we can get the core mode and the SPP mode. So now today, here you can see the color of the core mode is um, white and red kind of, and, and the color of arrow is kind of I don't know, it's kind of white maybe. So how you can change the color of arrow or color of the light actually is electric field. So I can show you how we can do that. So for that you have to go to surface, then maybe I told you before, from surface you can change the color actually. You can choose different color, which color you want to add your paper. You can use any color actually. Okay, so that's how you can change the color of I think color of um, surface. And then for a arrow surface, you can change the color of arrow surface as well. So for that, you have to go scroll down, and then here you can see that the color of the arrow is red here. So you can change it to blue. So then plot, you can see, okay, it's tough to see. So for that, what we can do, we can just increase the size of array. Okay. So you can see that by this you can change the size of array actually, and you also use magenta, yellow, or which color the color you want actually you can use that as well, black. So you can actually custom the color as well. So that's the thing. So whatever, we can choose any color from here. Okay. But for now, we can choose green, maybe it's fine. Okay, so this is our actually model. Okay, and another thing we can see how the uh, how the sorry surface is actually a deformation. So from height expression, uh, we can see this kind of figure actually as well. So here you can see that, okay, so here you can see, let me zoom it again. Okay, here you can see the um, model is working like that. So uh, sum of light is go through along with the gold surface, and maximum is light pass through the core actually here. Okay, so at the this is the core mode. Okay, so for SPP mode, let's see, this is the um, core mode of Y polarized light. Here you can see, and let's see the SPP mode. Here you can see that the SPP mode here, maximum light is passed through along with boulder or nano. Sorry, this is not SPP. Okay, this one is the SPP. Here you can see that maximum light is passed along with plasmonic material, and very small light is passing through the core. Okay, so that's the thing. Okay. And now what we can do, in my last video, what I told you that we will calculate, we will calculate wavelength sensitivity, amplitude sensitivity. Um, okay, for this video, maybe I will just calculate the wavelength sensitivity. So here we just calculate the conformance curve for refractive index 1.42. So maybe we can calculate the confinement loss for okay, just copy this on. Okay, so we can paste here. So here you can see that this is the conformal loss curve. Okay, just copy this on. Let me paste it here. It is the same thing, but just we copy the equation actually from there. Okay, now what I'm telling you that maybe we can calculate the conformant loss for 1.4 as well. So and then for 1.4 on, we can calculate the wavelength sensitivity of from 1.4 on. Okay, so let me do it. So now for 1.4 on, we have to change the RI. So from parametric materials, so Na, we have to change the value RI is 1.4 on, and in study from parametric shape. So let me check. So here, this in this figure here, you can see that for 1.42, this curve is for 1.42, and this curve is 1.41. Okay. So for 1.41, maybe is 940. So maybe let me check the resonance wavelength for 1.41. Okay, the resonance wavelength for 1.41 is 820. So maybe it can vary to 810 to 830. So that's why we have to just run in between this length actually. So for that, we can run from 800 nanometer to um, maybe 950 or 960 or 70. So I will tell that why we are simulating this curve from 800 to 970. I'll tell you that because the resonance wavelength for 1.42 is at 950, right? So that's why we have to choose we have to calculate the conformity loss at least till 960. Okay, then you can calculate the amplitude sensitivity. Right now I am actually trying to do trying to calculate the wavelength sensitivity. So for that you can calculate her to 900, but uh, at the same time I am also calculating the data for amplitude sensitivity. So run from 800 to 970, then compute. Okay, so as you know, it will take some time, so you have to wait until the simulation is done. So in the meantime, what we can do, um, we can just explore the thing here, the data table actually. So this sensor is in between 1.31 to, oh sorry, 1.32 to 1.44 refractive index. This range is actually the range of biological samples. So for example, blood, um, and sometimes this range actually shows the range of different diseases that can we can find from the blood. For example, cancer. So you can find out the different kind of cancer from your blood sample. So and as well this uh, from this range, you can calculate the refractive index of urine infection or any other things. Okay, as well the density of glucose. Okay, so that's the thing. So that's why this range is called biological samples range. Okay. So the sensor which can calculate the refractive which can show sensitivity between the range of 1.33 to 1.44. They called actually it's a biological biosensor. So that's the thing. So here you can see okay, for 1.32 the resonance peak is 560, right? Here you can see that this is the wavelength sensitivity. So the wavelength sensitivity is 1000. Okay. So the the thing is, and here you can see that 1.44, you can see that no, not analysis, because it's not showing the wavelength sensitivity. So you can tell that for 1.44 has does not have any wavelength sensitivity. Um, yeah, the thing is, if you want to calculate the wavelength sensitivity for 1.32, then you have to calculate with respect to 1.33. So I can easily help you to understand the thing. So for example, this is the curve of 1 point, for example, this is the curve of 1.32, and the resonance wavelength for 1.32. Okay, this is the x-axis. Okay, let's say the resonance wavelength for 1.32 is 560. So, and for 1.33, for example, the curve is like that. Okay, so let's say the resonance wavelength for 1.33 is 570. Okay, sorry, 70. Okay, so here you can see that the shift of resonance wavelength is actually we called this is the sensitivity of the sensor. Okay, so the shift of the resonance wavelength is the sensitivity or wavelength sensitivity. Okay, so here you can see by changing refractive index from 1.32 to 1.33. So we change the refractive index from 1.33 uh, uh, 1.32 to from 1.33. So the difference of the refractive index is equal to 0.01, right? So the change of refractive index is 0.01, and the change of wavelength or resonance wavelength is 570 minus 570 minus 560, right? Okay, so it's equal to 10 nanometer. Okay, so by changing 0.01 refractive index, uh, the change of resonance wavelength is actually 10 nanometer. So zero. So if we know the rules actually from 10 nanometer, right? The change of resonance wavelength is 10 nanometer. So if we change refractive index 1, then the change of resonance wavelength will be 10 divided by 0.01, right? So the sensitivity is actually 1000, right? That is the wavelength sensitivity. So this is the unit of this is actually nanometer. So nanometer, and the unit of this is refractive index unit, right? So refractive index unit, RIU inverse, right? So that's the thing. So this is the unit of the refractive resonance. Sorry, wavelength sensitivity, nanometer per refractive index. So I think you got it. So if the shift here, they actually actually use the shape of wavelength at 10 nanometer. That's why they found like this kind of result. But if you change the reflect wavelength, 1 nanometer um, uh, per 1 nanometer, then maybe you will find the resonance wavelength for 1.32 maybe at 557 nanometer, for example, and for this maybe you will find the resonance of wavelength at 565 or for example 671 nanometer. So then you have to differentiate between this. You have to calculate difference between 571 and 557, and then you have to divide with the sense of refractive index. So that's how you can calculate the wavelength sensitivity. Okay, maybe okay. So this wavelength sensitivity is actually we calculate for 1.32, the previous one. Okay, so the wavelength sensitivity of 32 with respect to 1.33. Have you got it? So that's the thing. So that's why we are trying to calculate the effective mode of 1.4 on, and then we will calculate the wavelength sensitivity of 1.4 on with respect to 1.42. Okay, I think you got it. So for that, we are calculating the data from 800 something nanometers. So we may shift it down. Okay, then write it equal and this one minus 10. Okay, so 830. So we are calculating from 800. So we need more shift actually. So it's called down more. Okay, let's scroll down it now. Okay, now from 800. Okay, so wait until the simulation is done. Maybe it's uh, 51% is done. Okay, so we have to wait until the simulation is done. Okay, just wait. Okay, I'm pausing the video right now. And after the simulation is done, I will come back again. Okay. Okay. The simulation is almost done, 99%. So we again back to the game. So uh, just wait few seconds. Then we'll get the results. Okay. And then we'll start again. Okay. If your simulation is done, then please wait for a second. Okay. Okay. Our simulation is done. Okay. So from surface height expression, we don't need it right now. And electric field, we need this one. Okay. You can zoom it. Okay. Understand it clearly, right? Okay. So yeah, we will start from 800. Okay. This is the core mode of expolarized light. Okay. Then we want to check how far it goes. Okay. So only to 800 and 810. So from global evaluation, okay, you have to click evaluate. So all the settings are the same as previous. You don't need to do anything. Study one, parametric solution, wall, outer solution. Okay, that's the thing. Okay, so you have to search the position of the effective mode. So from the bottom, fourth. Okay, okay, the position of it from the bottom is fourth. 1, 2, 3, 4. Okay, so click it and copy. And then you have to, I can paste it here from 800 to 810. So control, station transpose. Fine. No, you don't need it. Whatever. We don't care about it. Okay, then for 820, we have to search the core mode of explorized light. Okay, this, not this. Maybe. Okay, this one. Okay. So from the bottom, second position is the for on 820. Okay, and okay, this is for 820 only for 820. Okay, 820. We can just from the bottom second one, right? So we can copy only this uh, cell. Okay, something paste here. It's okay. Then we have to search for on 830. So maybe this one, I don't know. So let me search it. Okay, okay, this one. Okay, so let me search for other. Okay, let's go. Let's go. So this is the this is good actually. It's save for lots of time. If okay, that's good. Okay, this is the last one actually, and from okay we know where from where. So Control C, copy selection to and headers. Okay, Control V. So from 830, right? Oh, yeah, isn't it? Let me check from 830, right? Yeah, from 830. From 830 till end, right? 970. Okay, Control C and SP special transpose. Okay. Now what you have to do, you have to just copy this cell, Control C, and you can just paste it here. Control V. What you have to do, you have to just change this one. Okay. Uh, wait, this one. Okay. B2. And sorry, not B2. You have to change it to wavelength. Okay. This is actually the wavelength. So now we can scroll down it to here. So it's maybe done. Okay. Now let me check the graph. 1.4 on and 1.42. Okay. Yeah, it's perfect as the graph. Okay. Okay. Let me show you. This one is for 1.42 and this one is 1.43, right? So we got the graph as the paper. Okay. So we didn't calculate this part of this graph. You can calculate this part. Actually, it will take more time. That's why I'm not calculating. But for your paper, you have to calculate it. Okay. So that's the thing. So we just calculate. Okay. The right now we have to find out the um, maximum value from here. So for that, the easiest way is you can use in Excel, you can use conditional formatting, and the other is you can just take this on is the maximum loss. So this 820 is the resonance wavelength. In the paper, we can check for 800, right? For 1.44 on is the 100% perfect. We got the result 100% perfectly. 820. Okay, at 820, it's showing the resonance wavelength. But for 1.42, it's a shift bit, right? So for 1.42, the resonance wavelength of the paper was at 940, but in our in our reproduction we got at 800, sorry, 950. So it's not that much tough actually. So now it's time to calculate the wavelength sensitivity. Okay, so how we can just calculate the wavelength? Oh, I was going to telling you the how we can use conditional formatting. So you can click it here, conditional formatting, and from conditional formatting, um, uh, equal. Oh no. Sorry. Not this one. I'm sorry. Cancel. Okay. From sorry. From conditional formatting, you have to use new rules. Okay. From new rules. Uh, okay. You can use this thing actually. This is good. Um, So lowest one will show this color and highest one will show this color. It's good actually. And there are others way actually. Um, my this laptop is a bit slowing right now. So for that, part format only values that are open below. Okay, right, this one. Okay, not top 10. We have to calculate top one. Okay, so it will. Okay, and from here you have to set the color actually. So fill. We can use red as the color. Okay, and that's the thing. So okay, sure. So where we did it? This one, right? So new rules format top one person person of the selected room. Top one format. Okay. 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 Fine. So now it's work actually. So here you can see that you can just get the it will show automatically the maximum one, right? From if you just use the conditional formatting, and from here you can also use this conditional formatting as well. So new rules from data ranked and top one, and you can change the color from here, red. Okay, fine. Okay, so this is the maximum wavelength. Okay, so for 1.42, the as I mentioned before, I told you how you can calculate the wavelength sensitivity, right? So for 1.42, so wavelength sensitivity of 1.41, right? So wavelength sensitivity for 1.41 is equal to is um, the difference of sorry. Okay. The difference of resonance wavelength. The difference of resonance wavelength is 950 minus 820, right? 820 divided by the difference of refractive index. So the refractive index of 1.42 minus 1.41, right? So enter. So this is the wavelength sensitivity 13,000. So in paper, we can see that is sensitivity for 1.41 is 12,000 because the resonance wavelength for 1.42 in our case it shaped to 940 to 950. That's why we got 13,000. But in paper we got they got actually 12,000 wavelength sensitivity. So that's the thing. So that's how you can calculate the wavelength sensitivity of your work. So thank you for now. In our next video, we'll calculate. I will tell you how you can calculate the amplitude sensitivity. Okay, and maybe FOM or APM. Okay, whatever. Thank you. Thank you for now.